Our next lesson will be Vectors 1.3, and it will cover breaking vectors into components and component notation, and then using that to solve vector problems. And so starting things off is the techniques we've used so far to be able to solve problems where we're summing vectors have typically been add them head to tail, which will still be true here. And then once we get to that point is to use basically some form of trigonometry to solve things out, like say law of sines or law of cosines, or simple to straight trigonometry if it's a right triangle. Well, we're going to here use component notation, which is going to allow for a slightly different way of doing things, which in some ways adds steps, but in many ways makes the process of solving vector summation a whole lot easier. And so we start with a fairly simple statement. If it is the case that we said before that if two vectors can be added to produce a third vector, then it must also be possible to express an existing vector in the terms of two other sum vectors. In the same way that we could say this: if it's true that all real numbers can be added to form some other real number, like, 2 plus 5 equals 8, then it's also got to be true that if I have the number 9, I can express that as two other numbers, 5 plus 4, or 6 plus 3, 7 plus 2, something along those lines. The same thing is true for vectors. That, for example, if I have some vector which basically goes like, well, we'll take the one that's on the screen right now. So this one right here. I could write that vector in terms of two other vectors, one which goes this way and one which goes this way. If I sum those two vectors, I will get the black vector. That works just fine. I could do it in completely another way. I could say like here and then here. If I sum those two vectors, that will give me that first vector. In fact, it doesn't have to be two vectors. It could be 5 vectors, but 2 is what we're going to deal with here. But the thing is that we can choose what those two component vectors are. In the same way that you could choose that both 2 and 7 add 9, but so does 5 and 4. So it's 4.5 and 4.5. Is that we get a choice of how we get to choose how those vectors work. So let's say that we choose to make these component vectors such that they point along the x and the y axes. So I'm going to make my first vector along x, like this. I'm going to make my second vector along y, like this. And it is the case that these two vectors, my two red vectors, do sum up to make my black vector, my existing vector that's here. So we've got an x vector, we've got a y vector. And this ends up being useful because if you look at the picture that we have here, you will see that in doing this, we have created a very nice right triangle. And so if we have a right triangle, then we can just use standard trig to solve for what's going on. We don't have to worry about law of sines and law of cosines. Now, the problem is that whereas before, if we were adding two vectors, by reducing it to these two new vectors here for each vector, we now have 4 vectors. We have to add 4 vectors instead of 2, which seems like it'd be more difficult, but actually really isn't so bad. So let's take a look at a little bit that's attached to this, a component notation. So in order to write this out, a way of breaking these vectors into these x and y component vectors, we're going to talk about what's called a unit vector. So we can define a unit vector as being a vector which has a length of 1 in whatever unit system you're using. It's always just 1 long, pointing in the positive x direction. We're going to call that one x hat. Maybe a little difficult to see, but basically it's an x with a little hat on top of it, sort of a little up arrow. That's called x hat. The unit vector with a length of 1 pointing in the positive y direction is y hat. And so basically, so x hat is basically going to be a vector which points like this. It's 1 long. Y hat's going to be a vector which points like that. It's 1 long. Each of these is just one unit in length, and that's why they call it a unit vector. It's basically the vector equivalent of the number 1. Anything times 1 is itself. Anything times a unit vector is the same vector, as long as it's in the same direction. So this is basically, in a sense. So this is basically our unit vector here. Now, we could take this x hat and y hat, and if we multiply them by constants, we can get any vector we want to. If we have a vector that is in the x and the y direction, so if I have a vector that is 50 long in the x direction, I could simply call that 50x hat, because x is 1 unit long, and so x hat times 50 would give me a vector that's 50 long, pointing in the x direction. If I had one that pointed -6 in the y direction, like 6 backwards, like 6 off in the negative y direction, I could just simply say it's -6 y hat. That's a way of writing that out. It works just fine that way. Now, so we've got that. So multiplying x and y by constants, x hat and y hat by constants, we can get vectors in the x and y directions of any magnitude. We make it as big as we want, make them as small as they want. So if it is the case that we can write any vector in terms of an x and y components, as we sort of did before, where we took this vector and we said I can express this by writing out this and this. And if it is the case that any x vector can be written in terms of x hat, and so this would be something times x hat. Let's say that, for example, that this is 4 long. I call that 4x hat. And let's say that and the same thing is true for the y vector. Is that, say that's 3 long. I'll call that 3y hat. I can basically write out my vectors in this notation, and I can write out any vector in terms of x hat and y hat. So my black vector right here, I could just express as being 4x hat plus 3y hat. That's a way of writing out this vector, and it describes it completely. In a sense, what we're really sort of doing is it's like taking the coordinates in the Cartesian system, you know, where you have like 1, 3 or something like this. This one, in a sense, is 4, 3, as it starts at 0, 0, starts at the origin, and ends at some point 4, 3, which we'll describe as being 4x hat plus 3y hat. If this vector were to have gone the other direction, like let's say the original vector sort of headed off like this, and let's say that we have, so we draw out our components. Here's a component here, here's a component here. And so let's say that this one is 2 long. It would be negative 2x hat because of the fact that it goes in the negative x direction. And then we have other one we'll say is 2y hat. And so that's in the positive y direction. So this vector right here, we'd simply write as being negative 2x hat plus 2y hat. We can thus write out any vector we want to in this x hat and y hat notation, this component notation. And as we'll see, this turns out to be super useful in terms of adding vectors up, because well, we'll get to that in a second. Let's try this one first here. So we have a boat that sails at 12 knots. So it sails at 12 knots at 305 degrees. Write this in component notation. And so what we're going to do is that we start off with drawing out our vector here. It's at 305 degrees. 305 degrees is 35 degrees above 270. So that means that this angle in here is 35 degrees. Has a magnitude in here of 12 knots, 12 nautical miles per hour. Definitely not an SI unit, but we can still work with it. Okay, so we now want to take this vector and we want to break it into components. So we have an x component this way, a y component this way. And so let's say, how do we figure this out? So we've got our x, we've got our y. To figure these two out, well, as we said before, this is a right triangle. And since this is a right triangle, then we can go ahead and we can basically break this into components. Or we can, by using our fundamental trig functions here. So let's say we're going to look for x first. So x is the adjacent side to our 35-degree angle. We know the hypotenuse, and so if we have adjacent hypotenuse, that's going to be cosine. And so we're going to start off here by saying, to find x, we have cosine of our angle, which is 35 degrees, is equal to adjacent x over hypotenuse, which is 12. And so we get that x is going to be equal to 12 cosine of 35 degrees, just like that. And so, put it in the calculator, we say 12 times cosine of 35, once again in degrees here, at 9.8298. Not rounding too much yet. We'll get to that later, and this would be in knots in the x direction, as that's its component. But if you look very carefully, you'll see that x goes backwards. So whenever you're doing this, treat it like a triangle normally, and then look at the picture afterwards to figure out what the sign is. And so this case is going to be negative 9.8298 because it's going in the negative x direction. It's easier to do that than it is to basically set up your angles and try using 305 for this. Just go ahead and figure out your angles in the triangle, and then look at your diagram to see whether they're positive or negative. That's what I find to be the best way of doing that. Our second one here is going to be that our y, and so y is the opposite. Opposite over hypotenuse is sine. So we say sine of 35 degrees is equal to y over 12. And so once again, is that put it into the calculator here, we'd say 12 times sine of 35 will give us what our answer is for y, our y component. So the y component is 6.8829 knots. And so if we wanted to write out this vector in component notation, we would say that this would be quite simply equal to the x part. And look at significant figures. We have 2 here, so we're going to have 2 significant figures. So negative 9.8 x hat plus 6.9 y hat knots. So that would be one way of writing out this vector and a way of writing component notation. But still, we get to the question of why do we want to do this? Why would we take an existing vector that was perfectly fine by itself and split it up into 2 vectors, albeit 2 nice vectors that go in the x and the y direction? So to do that, let's take a look at how this helps out whenever we're summing vectors. So once vectors are written in component notation, they can be more easily added, as one can simply add each component to scalars to get the components of the resultant. So think of it like this. If I had 2 sets of vectors, the first one was 3x hat plus 2y hat. The second one was 2x hat minus 5y hat. And I wanted to find, those are my 2 vectors, and I want to find the total vector, the total component, the resultant. I could say this. Vectors that point along the x direction, since they point in the same direction, you can add them like scalars. And so when I do that, 3 plus 2 is 5. So I have 5x hat. That's my direction, the x direction. On my other side, on y, I have 2y hat minus 5y hat. Since they're in the same direction, I can add them as scalars. Minus 3y hat. Suddenly, I just added those 2 vectors. Don't have to worry about any of our trig. Don't have to, as far as when you're actually adding them up, don't rely on sines, law of cosines. All that goes by the wayside. You just add them up as scalars. The x's all add up, the y's all add up. It's a nice little trick that's going to help out in a lot of cases. So let's look at an example here. A pilot flies with an airspeed of 450 meters per second at 200 degrees, while a 15 meter per second wind blows at 345 degrees. What is the total speed of the plane? So we're looking for the ground speed here. And so we start off here with our pilot, which we're going to, here's our, whoops, horrible job of drawing an axis there. He's at 200 degrees, which is 20 degrees beyond the axis here, and so we'll draw that in. That's 20 degrees right in there. And he has 450 is his magnitude, so 450 right like that. And then what we're going to do is that we're going to add that to our wind speed, which is 15 meters per second at 345. So draw this guy here. 345 is just 15 degrees inside here. And so we know that's right there is 15 degrees. And we know it's also 15 meters per second. So we've got that. We know our resultant is going to be here. We could do this by, all of our previous stuff as far as, let's see, it looks like we could probably use law of cosines. But let's not do it that way. Instead of doing it that way, let's take these guys, let's break them into components. So I'm going to quickly sort of erase what we've got here because we can just redraw it here. So let's look at the first vector, 450 meters at 200 meters per second at 200 degrees. So here's our vector. It's 450 long. 450 long right here. If we look at our axis, we're going to draw the components. We have one component that goes down like this, one component that goes back like this. In this case, both of our components are going to be negative, as you can sort of see here. We also know that for our angle, we said it's at 200 degrees, which is 20 beyond, so we know that angle is 20 degrees right there. So if we wanted to find what our 2 components are here, for our y component, we're going to be taking the adjacent side divided by the hypotenuse. And so adjacent over hypotenuse is going to be cosine. And so I'd end up getting here for this side, for my y, is going to be equal to 450 cosine of 20. And if you multiply that out, we get 450 cosine 20. I get 422.86. 422.86 right there on x down here. X is going to be opposite over hypotenuse, which is going to be sine. So I'd get 450 times the sine of 20 degrees. Like that. And so we say 450 times sine of 20. And doing that, I get 153.91. Okay, so we now have our two components here. And so let's go ahead and write those out. And so for our first vector, we will say that we've got, let's see, so our x is 153.91. So negative 153.91 x hat minus, because the y is also negative, 422.8. 422.86 y hat. That's a y hat. That's an x hat. All right. So we have our first vector. Let's look at our second vector. Second vector is 15 meters per second wind blowing at 345. And so I've got this vector right here. It's going to point up in this direction. It's at 345 degrees, which is 15 degrees inside of 360. And so if I draw out my components here, we have a y component, we have an x component. We know this angle inside here is going to be 15 degrees. And so if we look at our two pieces here, we know once again that our, if we look at our we won't write next to them here, but we'll say the x direction here, our x hat, our x direction, is going to be, if we look at this, oh, I forgot to put the length to this, the magnitude. This is 15 is the magnitude on that. That would be helpful. So, to get our x component, that's going to be the opposite to the angle, and so opposite over hypotenuse is going to be sine, and so we get 15 sine of 15 degrees. And so once again, put them into the calculator, so 15 times sine of 15, and so we get that x component is going to be 3.88 right there. The y component is going to be, in this case, adjacent is the y length, so it's adjacent over hypotenuse, which is going to be cosine, and so it'll be 15 cosine of 15 degrees. And so 15 times cosine 15 gives us 14.49. 49. That doesn't look like a 4. That's a 49. So if we were to write this one out, we can see the x component is still negative. So instead of being positive 3.8, it'll be negative 3.88 x hat. And then for our next one here, our y is going to be positive. So 14.49, so plus 14.49 y hat, like that. And so now we simply just have to add them up. So going across here, we just say 153.91, negative 153.91 technically, minus 3.88 gives us a total of 157.79 x hat. And then it'll be minus pretty clearly here. So then we take negative 422.86 plus 14.49, and that gives us negative 408.37 y hat, just like that. So we have the overall vectors here. This would be a description of our total is 157.79 and negative 408.37. But it asks for the total speed. Speed doesn't care about direction, but it is looking for one value here. So what do? Well, we've already sort of got this guy here. We know he goes it's going to be negative 157.79 x hat. And so we know in the x direction, he's going to head out this way by a length of negative 157 or 157.79, like that. And then he's going to go south. Give me the next piece right here, 408.37. 0.37. That's not a horrible way of writing that, but you get the idea. And the component, or the resultant of those two is going to be this one. That's the one we're looking for. And so it's just, that's a right triangle. It's Pythagorean theorem time. So 157.79 squared plus 408.37 squared. And then once we've got that, we take the square root of it. And so I get 437.79 is going to be what we have here. Significant figure-wise, we have 450. That's two significant figures. 15, also two significant figures. So this one's going to be, should be two sig figs on this one. There is some addition that goes on here, but it doesn't look like that's going to affect it the way it sets up here. So this is going to be 400. So our final answer here would be 440 meters per second is going to be his total speed. So you can see this does keep us from having to do, it does require a lot of math still with it, but it does keep us from having to set up and do our law of sines, law of cosines. And so it's useful for that reason. So let's try another one here. Just a little more practice while we're at it. So three men push on a table, the first with a force of 97 newtons at 30 degrees, the second 45 newtons at 320, and the third at 70 newtons at 350. Which direction does the table go? And so in this case here, we'll take the top view on this. So here's our table. We know the first one pushes at 30 degrees, and so that's going to be up like this. So I'll do my little axis right here so we can sort of see here. So 30 degrees in here, that's 97 newtons. Our second one at 320. So 320 would be 40 degrees back. So that's 40 degrees in there. And he's 45 newtons. Shouldn't have drawn it that long. 45 newtons. That doesn't look like a 45 at all, but you get the idea. And the third one is 70 newtons at 350. So 350 is going to be inside of this, up like that. And so this is basically what's happening. We know the table is going to go somewhat sort of northward, but it's probably not going to go due north. And so we could do this. We could add up all these vectors head to tail, but let's just try doing this component-wise. Let's break these guys up. And so we have our first one, 97 newtons at 30 degrees. And so that vector is going to look a little bit like this. And so we've got that one in here. We're going to break it into components. And this time what I'm going to do is I'm just going to shift it over a little bit. And so doing this, if that was actually straight up there, then remember that this little angle down here was 30 degrees. That means this one's going to be 30 degrees just by trig, just to make things a little bit simpler here. So we've got that little sketch right there. We know he's 97 long. We have, let's try our next one, which is 45 newtons at 320. And so he's going to be back along this one right here. And see, he's 45 newtons. And so similarly, we'll draw him out into components. So we have an x component, we have a y component. For this one right here is that if he is at 320 degrees, that would mean he's 50 degrees above the 270 mark. And so that means this right here has got to be 50 degrees right in there. And our last vector is 70 newtons at 350. And so in this case right here is that if he is at 350 degrees, that would mean 350 is just 10 degrees. I guess I probably ought to draw that one a little bit higher up. Let me get that, make it a little more obviously 350 degrees. That's almost 360 degrees. So he's more like that. It'll work the same way. You just need to get a general idea on your picture. It doesn't have to be super precise. And so like that's not very super precise, but you get the idea. So we've got that one here, and he is at 70 newtons. So newtons, newtons, and newtons. So let's break these guys into components. So let's look at our first one here. We'll go ahead and sort of label these out just so we know what we're doing here. We've got person 1, person 2, and person 3. And so for this, let's look at person 1. So for person 1 here, that we're going to have, let's look at the x-coordinates, and then let's look at the y-coordinates. So for person 1, that if we look at this, we've got that for the x part is the opposite over hypotenuse, because the x part is the opposite side. So opposite over hypotenuse is going to be sine. So we'd say this is going to be 97 sine of our angle, which is 30, like that. And so whenever we do that, we get their x component would be able to plug in the calculator. So 97 sine 30, 48.5, like that. For our y component, it's going to be 97 cosine of 30, Noticing a pattern here? So it's just 84 even. All right. Now looking at direction here is that the 48.5 is positive x direction. The 84 is positive y direction. So both those are positive. So let's look at our second one here. So second guy is going to be the x component is going to be the adjacent, and so that's going to be cosine. And so we have 45 cosine of 50 degrees. And so we plug it in once again, 45 cosine of 50. And so to do that, 28.93. Now in this case, this one is backwards. That will be negative. For our y, it's going to be 45 sine 50 degrees. And so 45 sine 50, because of the fact it's the opposite side, 34.47. Now this one's up, so it's going to be positive, so we've got that. Our last one here, get that into components here, is that, forgot to put the angle on that one, didn't I? So we know that this one is at 350 degrees, and so that means that it'll be, this little angle in here will be 10 degrees, which means that angle has to be 10 degrees. So that's what we're going to start with. You always need to put those in. Difficult to do without that angle. In fact, the proper term would be impossible. So in this case right here is that for the x component, that's the opposite side. Opposite over hypotenuse is going to be sine. So we have 70 sine 10. And so we type that in, 70 sine of 10. And so we get 12.16. In this case right here, that x is still going to be negative because it goes in the opposite of the positive x direction. And our other one is going to be 70 cosine 10 because it's the adjacent side. And so 70 cosine 10 gives us 68.94, which is going to be positive as well. So to work this out, we add all these up. So if we add up all our x components, which is going to be 48.5 minus 28.93 minus 12.16, doing that, we get an x component of 7.41 x hat. Then for y, we add those up. So we have 84 plus 34.47 plus 68.94. And we get a total of 187.41. Like that. Sketching this out, we know it's going to be positive x, so 7.41. Then we have y. Notice when we do this, we're adding them head to tail. 187.41. Looking for the resultant, our total here, the direction the table is going to be like that. So that's going to be our vector here. We could figure out the total force if we wanted to using Pythagorean theorem. But in this case, it asks us for the direction. And so to find that direction, we're going to need to know what this angle right in here is. That's our theta. And so to do that, we have opposite, we have adjacent. Whenever you're doing that, it's going to be tangent. And so to set this up, we would say that tangent of theta is going to be equal to opposite 187.41, it's an 8, over adjacent, which is 7.41, like that. And so we'll have to take arctangent of that. So we'd say arctangent of 187.41 divided by 7.41. And in doing so, get 87.73 degrees. Now, the problem that we have here is that that angle is this spot right in here. To find what we're looking for, we want a heading. Heading would be this angle. And so since those have to add up to 90, what we could do is we take 90 minus that answer. And so doing so, we get 2.26 degrees. Since on degrees we round to the nearest tenth, our answer here is going to be just 2.3 degrees. And so the table would be moving at 2.3 degrees, which would make sense because it looks like these guys are trying to push it straight up, and straight north, and 2.3 degrees is not very far away from straight north. So that would fit in quite well there.